at its highest. Well, there's two ways to do this. The algebra way is to look at the height equation, and we want to find its maximum. Well, we have to have a calculator to do that. We want to know what x value puts this graph at its highest. So let's do that with the calculator. Second calc, that's a maximum. Remember how I have to get to the left side of it first. It's asking for the left boundary. Hit enter. Now it's asking me to get to the right side of it. Now slide back, get close to it. 1.999997, so 2 seconds after. Well, how could I have used calculus to answer the same question? Well, we have to remember the connection. A derivative at a max, because the tangent line is flat there, the derivative is always 0 at the max. All I would have had to do was take this derivative equation and set it equal to 0. So this was on the graph, the distance graph of h of x. If you take the velocity graph, which is negative 10x plus 20, see where that equals 0 at, because if the derivative is 0, the original function was either a max or a min, and we can see that it was a max on that graph. Subtract 20, negative 10x equals negative 20, divide by negative 10. So at 2 seconds, the derivative was at a 0, so that means the book was at its max. Okay. So let's talk about that, the relationship between a function and its derivative in the next example. Example 9. I'm going to give you a function, and I want you to be able to sketch a reasonable graph of the derivative without the equation. And this graph is going to be a piecewise. It's a cubic with a linear. Okay, so there's our original function. Now we're going to sketch reasonably the derivative. So the things to remember, the first thing you should do, find all the max and mins, because you know that the derivative is 0 at each of those spots. So find max and mins on the original function. Then you know that the derivative values equal 0 there. So I've got a max here. So that means my derivative is going to have a 0. It's going to cross right there. I've got a min here. I'll put it at the origin. So my derivative graph is going to cross there. Now, if the original function is increasing, the derivative function values are positive. So, and we read from left to right to see whether I'm going uphill or downhill. So from here, when I read left to right, this whole graph is going up. So that means for all of these x values here, my derivative graph has values that are all positive. They've got to be up in the air here. The other thing to remember is if f of x is decreasing, then the derivative values are all negative. And you can see that's what happens here. After I hit this max, now all my values are going downhill. So that means all of the x values in here, all the way from this 0 to this 0, they're all going to be in the negatives. And I've got a touchback here. So that just tells me that this thing scoops down below and comes back up to hit that 0. Then, after that min, we're on our way back uphill again. Up, 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 until I get to this. So I'm positive all the way up to there. Now here, I'm decreasing again. But what's different about this decreasing as opposed to this, I should have made that a little bit rounder. Here, my derivatives were changing because it was a nice smooth curve. Here, it's very linear. The slope is the same all the way through here. At every point, the slope's the same because this is a line. That means my derivative values are all the same negative number. What negative slope is that? I don't know. I just know that it's down here in the negatives. So it's linear there. Negative, same number. There's a reasonable sketch for the derivative of that function. Okay. We're almost there. This 29 to 32 in your book. If you look, it says for problems 29 to 32, tell quickly whether f of x is increasing or decreasing at the given value and how fast. Anytime you see how fast, that's a rate of change, that's derivative. Well, quickly means use your power rule. So what you're going to do on all of these is find the derivative, plug the number in afterwards. If the derivative value is positive, it's increasing at whatever number you get, that rate. If it comes up negative when you plug the number in, then it's decreasing. So, let's just check out one of those. Let's look at number 31. So you won't have to do 31 on in your homework. We've got f of x equals x to the 1.5 minus 6x plus 30. And we want to know two things. Is f of x increasing or decreasing? And how fast at x equals 9. So, we need the derivative to tell how fast anything is. So that's 1.5 comes down as a multiplier. Subtract 1, we've got a half left there. Minus, that's an exponent of 1. Bring that down, you get 6. X to the 0, anything to the 0 power is a 1. That goes to 0. Now we find f prime of 9. 1.5 times 9 to the 0.5 minus 6. Well, that's just square root of 9. Square root of 9 is 3. 3 times 1.5 is 4.5. 4.5 minus 6 is a negative 1.5. If you need to pick up a calculator there, go ahead. I just know that the 1/2 power is square root, and 9's a nice square number. So, it is decreasing at this rate. I can't put any units on it because there was no story problem to tell me what those units were, what values x were in and what values y were in. So it's decreasing at that rate. Example 11. Oh, lots of examples today. Show that each max and min on f of x corresponds to a 0 on f prime of x. So we're going to be showing this on the calculator. So we've got x cubed over 3 minus 2x squared plus 3x plus 9. Okay, we'll be graphing that in a minute. Let's do the derivative right now. Remember, think of this as 1/3 x cubed. So now derivative, the 3 comes down, 3 times the third is 1, x squared minus 4x plus 3 plus 0. So if we graph this original one, we'll graph this one, we will have it find max and mins here, and we'll trace to those x values on this, and they should be the zeros here. So, and it's all going to be calculator work. Y equals x cubed divided by 3 minus 2x squared plus 3x plus 9. Okay, looks like we want to see up here just a little bit more and a little less of this. So window, we're going to decrease the x. We're going to go -5 to 7. Y's, maybe -5 to 15. Okay, so that allows me to see there's a max here and a min here. Then we're going to graph y equals the derivative equation, x squared minus 4x plus 3. Okay, these two zeros should correspond to that max and that min. So let's do that. We'll second calc. Maximum is what we're trying to find. I'm on y1. Let me get to the left. Enter. Get to the right, enter. Go back. So it's a max when x is 1. So if I trace to 1 and I jump to y2, that what happens to be my 0. 1, 0. So prove that one. Now we'll get back on y1, do the same thing for that min. I want to calculate a minimum. Stay to the left of it. Get to the right. That's happening at about 3. So if I trace 3, jump to the other graph. Oh, it got off of 3. Trace 3. There it is. Oh, jump back up there. Trace 3. I don't know why it won't stay down there. But I think we can see that that's what's happening. So the whole goal there, and we should probably do that, practice that sketching again, because it does seem to be a skill that's lacking. So we had this nice cubic function. The cubic functions have that little snake move in it. And you know when you take the derivative, it goes down by 1 power, bringing us down to that quadratic. So the max here and the min here are zeros. Just like before, it's decreasing through here. That's what's giving us our below the x-axis negative y values. Now it's increasing. And here it was increasing. So you get that nice parabola. Okay, homework.